This talk is about reducing false positives and fast screening. It's a talk by Future Synthesis and the Lens Lab, Department of Physics and Technology at the University of Norway, UIT. First, I will discuss very basic concepts, but concepts that I think are important to refresh before we discuss this. What is the population X of a study? For example, if we have people in the US, the people are X, okay? People are X. So one person, 2, 3, 4, to the 330 million approximately that we have in the US. So that is the total population in the study where we investigate, and that's the key, we are investigating something about this population X. In this case, a condition C, that's the condition. Each subject E, or sample E in the experiment, is an element or sample of the study. So every person is a sample or element of the study. The population is X and the condition is C. So positives will be the number of elements or people with condition C in X. But that's precisely what we don't know. So there is indeed a population X, there are people in the US, and these people either have C, and they are positive if they have C, or they do not have C, and then they are negatives. And the total amount of people, X, are P plus N, so the number of positives plus the number of negatives. But that's precisely what we don't know. We know how many people we have in the US, but we don't know how many have the condition positive and how many do not have the condition N. So the issue here is that we know that we have X, that is the population. For example, the number of people in the US is X, is a number, right? But we also have a predicted population X prime. That is, while each sample or element in the population either has the condition C, which means that it's a positive, or does not have the condition C, that is, it's a negative, we only know the population X prime, where X prime is not the same as X. So what is X prime? X prime is the prediction, or corresponds to the prediction for each element or sample in X. So what we predict about people in the US, which is each element, gives us X prime. And X prime is made of positives prime, which is the number of elements predicted to have C, and the negatives N prime, which is the number of elements predicted to not have C. So we have X prime, which is P prime plus N prime, but the ones that we predict to have the condition is not the same as the elements that have the condition, which would be P. Not only quantitatively, in the sense that it's not the same number, but maybe we get them wrong. So people that are negative in the population, we predict them to be positive, and people that are positive, we predict them to be negative, and also maybe not even the number is correct. Maybe we have 10% of people that are P, and we predict P prime, 20% of people to be P. So P prime would be 20%, but also they do not correspond to the actual people that have the condition. So that's the problem. And this is very important to understand because we need to understand how to make a model. And this is what I will discuss now. In summary, we have true and false positives and negatives. True positive is an element of X that has been diagnosed as P, and it is truly P in X. So if we say it's the element in X is P, and it is truly P in X, we call it true positive. True negative, an element of X, an element E or sample or a person in X in the population that has been diagnosed as N, as negative, and it is truly negative in X. False positive is that which has been diagnosed as P, as positive, but in fact it is negative. And false negative is an element that has been diagnosed as negative and in fact is positive. The issue here is that we don't know how many people are positive and how many people are negative. So how can we know how many true positives we have if we don't know who is positive and who is negative? And that's the actually the first part of the problem that I will discuss now. If we have false alarms versus missed alarms, we have problems either way. So a false positive is a false alarm, a type 1 error. So if we say to somebody, you have the condition, but they do not have the condition, in fact, it's a false positive and it's a false alarm. Let's assume this, that nobody has the condition, and we say that 10% of the population have it. We are creating a false alarm in the population because in fact nobody is positive, but we say that we have 10% of positives. So that would mean that X prime is not the same as X. It's not the same, not only that, but it's not the same by far. It's not the same 0% as 10%. We also need to take into account context. For example, to say that you have cancer is a very bad thing, but to say, for example, whether you have a pencil in the pocket, that is irrelevant almost. But if we are dealing with something very serious, like saying that you have a condition, then we need to take into account the fact that it's not the same to be positive as to be a false positive. The same happens with false negatives. And that's a missed alarm, type 2 error. It's also bad because if in the population X, someone is diagnosed as negative and in fact they are positive, you create the state of missed alarm in the sense that people think that they're fine, but in fact they are producing a condition where there will be an alarm because they will be thinking that they don't have the condition and they in fact have it. Cancer, for example, you wouldn't pass it on to other people, but if you can infect people, like with a coronavirus, then of course if you have the condition you can infect people, it's important that you know. So you want to also get rid of false negatives. So how do we make models for this? And this is the important part. This I will write model here because you don't know the number of true positives in a population, right? So what you want to know is true positives versus positives, and that's called true positive rate or sensitivity, and it's the number of positives that you detect versus the total number of positives, which is the same as true positives plus false negatives, because the total number of positives in a population is the people that you say that they are positive and in fact they are positive, plus the people that you tell they are negative but in fact they are positive. So that ratio is the sensitivity. But how do you know? And this is key. To make this ratio, which implies that you can tell if a diagnostic test or a test is good, you need to have high sensitivity. So you need to get many true positives and reduce the amount of false negatives that you get. So if you are positive, I want to say that you are positive, but if I say that you are negative and you are in fact positive, this is a mistake, so I want to reduce this number. And how do we do this? What you need is to make sure that you make the model through a classification problem with a subpopulation where you truly know in advance who is truly a positive and who is truly a negative. If you don't have this very well established, then it's very difficult to know if your test is good or bad. What does this mean? That for me to know how good the test is, I need to know in advance from a subpopulation, from people that I'm going to do the test to. These people I need to know before I apply the test if they are truly positives or truly negatives. And only then I can know the TPR, or sensitivity, or the true positive rate. The same happens with the true negative rate. So it's the number of true negatives divided by the total negatives. And for this reason, I also need to know the true negatives and the false positives. Okay, so I need to test it. So if I know who is in fact in the population negative and who is in fact in the population positive, then I can know if my test is good in terms of specificity, which is TNR, true negative rate. What is the problem? And that's why I've been explaining all this, that you don't know in the population who is truly a positive, and you don't know in the population who is truly a negative. That's in fact the problem. If we knew who is positive and who is negative, you would have solved the problem before you even need any test. So what you need to do is to take a subpopulation, so some people in the population, and in these people that you take, you need to know for a fact, or as well as you can, how many are true negatives and true positives. And only then you can make a test for your test. So you can test how good your testing device or diagnosis test is in comparison with others. For example, if we have a diagnostic test that has a TPR of 0.5 and another one that has 0.8, you would say, okay, so I'll get the one that gets most true positives and reduces false negatives. That's what you might say. But in fact, every test has a sensitivity and also a specificity. So if you have high sensitivity, for example 0.8, maybe you have very low specificity, maybe 0.1. So is this good to have 0.8 and 0.1? Or for example, if you have 0.5, maybe here you have 0.9. So which one is best? 0.5, 0.9, or 0.8, 0.1? And what I want to discuss here is that whatever you take, whether you take one which has 0.5 sensitivity and 0.9 specificity, or the other way around, 0.8 and 0.1, what matters now is to know what you have as well as you can, and now to design an experiment to say, okay, I'm going to use my test as well as I can to get as many true positives as possible and as many true negatives as possible, to reduce false negatives as much as possible and false positives as much as possible. Even in here, is it better to reduce false negatives or false positives? It depends on the context. You need to understand what type of problem you're dealing with, and that's not something I'm going to touch here, but I'll proceed explaining all this problem. If we search in Wikipedia for sensitivity and specificity, we actually find all the terms that we might need. So we have sensitivity, that they call also recall, true positive rate, also specificity, which they call selectivity also, true negative rate, precision. We might have a negative predictive value, false negative rate. So, but we see that it's all fractions. So it's all on top something and the bottom has something else. So if we know the true negatives, true positives, false negatives, or false and false positives, we can calculate all this. But this, when you create a model, this is how good the test is. That doesn't mean that you will do well in the population, because when you testing your device, you are testing your device on a population that you know. What you want to know is how well that test does for the population that you have. And you might say it doesn't matter if the test is good, it's irrelevant, it will do well anywhere. And that's not the case. It will not do as well in one population as it would do in another population. And we'll see now, and also it depends on context as well. what you want to optimize, if you want to know very well, for example, the true positives and reduce false positives, you need to go one way. If you want to reduce false negatives and improve true negatives, you need to go another way. So it depends on what you want. So the first thing is, what is it that you want and why? And then you need to design your test around that problem. What is it that you want? So here we'll go for an example of what we might want to improve, and I will discuss that now. For example, as example 1, classification error. What would that be? Typically, when you tell people that you have an error, for example, 1%, people say, wow, so that's quite good. For example, imagine that I say, in my bank account, I've got $1,000 with a 1% error. That's quite good, because it's like I either have $990 or $1,010, something in between. It's okay for money. I would say it's quite fine. But sometimes it's not that good. For example, let's do an example here, and that happens a lot with diagnostics. Okay, so what's the error? First of all, that type of error puts on top the false positives and the false negatives, and the bottom is all the population. Okay, so for example, if we make 1 out of 100 predictions that we make, because we have 100 samples or examples, and one of them we get wrong, it's either false positive or a false negative, and there's 100, so we got 99 true positives and true negatives, so that's a 1% error. Okay, you multiply these times 100 and you get a 1% error, because I only made one mistake. So you would say that that's very good. And the accuracy is actually the correct predictions divided by the total number of predictions, which is true positives plus true negatives divided by the total population, which would be here, for example, I made 99 correctly out of 100. So 99 I got right out of 100. So you would say that that's very good. But many times that's actually nothing. It doesn't mean anything. You might be surprised at this, but it's important to understand this. And this tells you that context is very important. So this example is a very good example, because it shows that context is important, and you need to know before you use a machine or a testing device, you need to know very well what it is that you want to do. So let's see. For example, if we have 100 elements in our sample and 99 are cancer negative and 1 is cancer positive, and that means the following. It's very simple. So imagine a village with 100 people, yeah? And out of these 100 people, 99 people do not have cancer, yeah? They do not. Let's do it like this, or a 0. And 1 person has cancer, yeah? So let's put a 1 here. So we could say nobody has cancer. So we say, okay, so in this village of 100 people, nobody has cancer. How many mistakes we made? 1 out of 100. So the error is 1% and the accuracy is 99%. But we in fact did nothing. We just went to that village, or maybe we didn't even go. We said, okay, take that village. It's likely that nobody has cancer there, so let's say 0. So it's a very good classification error. In terms of error, is a very good to classify, a very good way to classify numerically, but it's meaningless. The meaning is not there, because you're not saying anything about the people that have cancer. So let's see in more detail what this means. So is this meaningless? So if the error is 1% and the accuracy is 99%, the error is in fact the number of elements with condition C, which is 1%. So we are just saying that as long as we know how many people might have a condition, we just say that that's the error, but saying that nobody has it, for example. But we fail to get the important cases. The important cases is who has cancer. So we need to get some true positives, otherwise we're missing them all. These classifiers are useless then. They're useless for us since we will miss all the positive cancers. They tell us nothing about cancer other than this. It is unlikely that one given element of the sample has the condition C, okay, or being positive. So let's now go into the misunderstanding of classification in terms of, for example, sensitivity. High sensitivity, is it good always? So we have a testing device that is extremely robust. We have very high sensitivity. We've seen, for example, that the PCR might be very good in terms of getting positives, and it gets maybe very few negatives, false negatives and false positives, for example, but maybe it takes too long to perform them. So that's another thing, and that's context again. What might happen here with the PCR, for example, is that the disease is fast in spreading than the time it takes for us to perform the PCR test. This is another type of context, right? We need to take context into account. In any case, in terms of high sensitivity, that might be the case also. We need to understand very well what it is that we're doing with it. So high sensitivity is a function of true positives and false negatives. You see that here, false positives, in principle, make no sense because it's not a part of the function. So TPR, okay, TPR, as we said before, is true positive divided to true positive plus false negative. It doesn't care about false positives. So we might have very high sensitivity, but we might be getting a lot of false positives. For example, the opposite is what we said about cancer, right? That we got all false negatives. For example, in the village, one person had cancer, so we got one false negative, which was 100% of possibility of getting negatives. We got them all, which was one only, but because there was only one, getting one wrong was getting all wrong. So that's the same with sensitivity. We might get very high sensitivity, but we might get many false positives also. So the ratio of positives P that will be assigned positive is this, is the sensitivity. That's what we know about sensitivity, okay? So what happens here? Imagine that we have 0 positives in our underlying population, and this is an example of where this could go wrong. Even if we have high sensitivity and 0 P, 0 positives in the population, we will get false positives, right? So imagine that, for example, in a population, nobody has cancer, okay? But we have a test that has very high sensitivity. If that means that we get many true positives out of the positives, but we have no true positives in this population. For example, in a village of 100 people, we have 0 positives. So high sensitivity means nothing here because nobody has cancer in this village, for example. But because we'll get false positives, for example, imagine that it does very bad, this test does very bad in getting false positives, we say, well, not very bad, 2%, for example, we'll say, okay, 2 people have cancer, but they are false positives. So even though we have very high sensitivity, in a village of 100 people where nobody has cancer, we'll say that 2 people have cancer. We'll say, and by the way, because we have very high sensitivity, if we tell you you are positive, it's very likely that you are positive because we have very high sensitivity. So we detect the positives very well. That's what we could say, right? We could say, look, because our testing device is so good that if we have a positive, we'll find it because the ratio true positive divided by positives is very high, and we tell you that you have cancer, you have it. It's very likely you have it. But look at this case. The village has 100 people, nobody has cancer, we take the test and 2 people are positive. That's because they are false positives, and that tells you nothing about it. So this test, in this way, doesn't mean anything. It doesn't say anything about false positives. And then these people will go home thinking, oh, I've taken this test with very high sensitivity, and they told me I have cancer, and the test is extremely good because it detects almost all the positives in the sample or in the population, so I have cancer almost for a fact. But in fact, they don't have it. Nobody in the village has cancer. So this is one of the examples where we might get misunderstandings. In conclusion, regarding error as classifier and uneven sensitivity, higher accuracy and low error do not mean that we are dealing with a good instrument. So the instrument is good, yes, but are we doing the experiment well? Are we interpreting the results? Is the design of our experiment good enough? A diagnostic test or mathematical algorithm for any population is not good for every context. So we cannot say, let's use this machine for any context just because the machine is good. That is, that an instrument is precise and accurate does not mean good results. Doesn't mean that. Maybe we are dealing with a highly skewed data set, and I will speak now very briefly about this. Many elements are either positive or negative, and we are biasing toward one or the other. So then we have skewed classes, and that's actually the problem, and that's a very well-known problem. A skewed class, and I took this from the machinelearningmedium.com, which is actually taken from a course in machine learning. Anyway, what we get in this definition is that skewed classes refer to a data set wherein the number of training examples belonging to one class outnumbers heavily the number of training examples belonging to the other. But we see here that that's for the training set. So they're worried about training sets. But it's not just about training set, that is the set that you use to make a model. For example, in the case of the fast scanning or fast tests, we might get a subpopulation where we have a subpopulation, let's call it XS. Let's assume that we know very well the true positives and true negatives in this population, but the ratio might be different, and we'll see this now. In any case, in this skewed population, we get negatives, all that. Okay, so all these is negatives, and all this, and these are the positives. So these are examples like the one with the cancer that we said. In a village, one person has cancer, or in a village, nobody has cancer. And we always have problems when we're testing with a device that has good sensitivity, even good specificity. It doesn't matter. We need to understand what can go wrong, and we need always to interpret the data and understand what's a positive outcome and what's a negative outcome. And what I want to discuss here is precisely that. Let's see the next slide. Is that even if a testing device tests on X, for a let's put here S, subpopulation, because one thing is the population, for example, everybody in the US, another thing is a subpopulation, for example, the people used to test a device or a testing device. So we have a subpopulation where we know very well here, for example, in this one is here, this one, where we know very well the positives and we know very well the negatives, and we might say, okay, so for the training of the test or testing our device, let's take 50% of people that are true negatives, okay, and 50% of people which are true positives, and we know that. So we know this subpopulation very well. Another thing is dealing with errors in what we know about the subpopulation, but let's say that we know very, very well the subpopulation that we're working with to test the device, and we decide to be neutral. We say we take 50% of true negatives and 50% of true positives. So for example here, if we got out of the negatives, if we got true negative rate, for example, true negative rate, we got 40% of these, we would get 4 divided by 5, okay, 40%, so 80% of, if we get 40%, 40% of the negatives overall, we get 40 divided by 50, okay, which is 80% multiplied by 100. So the true negative rate is 80%. That means out of the negatives, out of 100 negatives, we'll get correctly 80. So that's 80%, okay? So that's the specificity. And for here, let's see that the true positives divided by the overall positives, let's say that we get, for example, I don't know, let's get 30, or to make it simple, let's get 25. Okay, so we get all this. So 25 divided by 50, it's 50%, okay? So our sensitivity is 50%, and our sensitivity is 80%. So we got all these wrong, that in the testing device, we got false positives. This would be false positive. And this, we got here, all this, half of the 50% that were positive, we got false negatives, okay? And then we say, okay, so that's our testing device. We trained it with a population X sub S that we knew in advance, but now we're dealing, and that's the point here, with a population that we do not know at all. So at all, or maybe we don't know as accurately, okay? So how many true negatives are here? We don't know. How many positives are here? We don't know. Let's use any testing device only because it gave us very high sensitivity and very high specificity. That's the problem. We shouldn't do that because we need to know in advance what it is that we want to find. So are we very concerned that we'll get many false positives? Are we very concerned that we'll get many false negatives? Are we very concerned that maybe out of a population of, I don't know, 100 million, maybe 10% have a condition and we'll miss 90% of these, but we'll get many true negatives and very few true positives, but we care about the false negatives, for example, and the true negatives. This is the issue. We need to understand very well what it is that we want to find in the experiment. And now I'll give an example of this. What I want to do now is a very simple example. Let's assume that they give us a device that they've tested on a particular training set or examples, and they tell us that the specificity is 90%, and we have a TPR, true positive rate, of 60%. So now I'll do only 6 cases because I want to explain this in detail, 3, 4, 5, and 6, and I want to explain what this means. So now we have a population X, and we don't know that this is 0. We don't know this is a 1, 0, 0. So this is the true, yeah? But this column here, we don't know. But I know here because it's an example, but in real life, we don't know. So let's see what would happen if we didn't know. This is an example of what could happen if we did the test on these people. So with these numbers, 60% and 90% of specificity, it's possible that a 0 turns into a 1, so that's a false positive. A 1 turns into a 0, that's a false negative, and that's because this is not 1. If that was 1, then that couldn't happen. And if that was 1, also it couldn't happen. But because it's not perfect, it's not truly perfect, so we get that a 0 turns into a 1 in X prime here, or X star, in the first cycle, okay? We'll perform multiple cycles. A 0 turns into a 0, so that's a true negative. 0 into a 0, true negative. 1 into a 1, true positive. 1 into a 1, true positive. Okay, so what does that mean? That in fact we had 3 positives in the population and 3 negatives, but we got 1 false positive, 1 false negative, 1 true positive, and one true negative. So the true positive rate, it's here 66, okay, because we got 2 out of 3. The false positive rate and the false negative rate, which is something I didn't discuss, is false positives divided by n and false negatives divided by p. We get 0.33, 0.33, and I repeat, these numbers we cannot know because we don't know the real population, so we don't know how well we'll do in the population. That's why this is like a mock-up of a simulation. I will perform a simulation with Matlab, and I'll show you what happens in a real simulation. But well, we don't know in principle, but that's what could happen. But we wouldn't know these numbers, okay? We rely on this. We think that this is what we'll get, but in fact we get something else because we don't know the true population. But here, that's an example of what could happen. So what could happen is that the true negative rate would be 0.67. So what happens now if we don't care about the zeros anymore and we persist and we insist in these ones? If somebody tests positive in the first cycle, we go into a second cycle. And now the one that was a false positive again is a false positive, for example, but one that is was a true positive, now it gets into a 0. So in the second go, only because we take only the positives, we do actually worse. So what's the point of going again in the positives if we might do even worse? That's because in the long run we'll get rid of the false positives, of this one here, and that's what we'll show. We'll get rid of that because eventually, because this 0.9 and this 0.6, eventually the false positive will go. And indeed, we did worse in the second cycle, but in the third, we see that we do better because we got rid of this one. And it's very likely that in the second go, we won't get rid of this one, so we'll get it correctly. So at the end, we only got one true positive. So what's happened here is that true positives, we only got 0.33, so we did worse than they tell us here. Okay, so we did worse. I'll remove some of this to show. So we did worse because, let me see with this. This tells us 0.6 and we get 0.3 because of multiple cycles. But we did very well removing false positives because we got 0. Okay, so 0% of false positives, but we did worse in the true positive rate than the machine would tell us, okay, because we did multiple cycles. So in summary, what happens is that if we keep testing the positives, the false positives can go only down, the false negatives can go only up, so we'll do worse in the false negatives. The true positives can only go down, we'll also do worse, and the true negatives can only go up. So we'll get, if we keep testing on the positives, we'll get more true positives, we'll get less true positives, but we will reduce the number of false positives. If that's what we want, this is one way to go, okay? Another thing is to understand why one would do this thing. What I want to discuss now is a simulation that I will do in Matlab, showing what happens with multiple cycles, and instead of doing 6, let's take for example 400, and the good thing about Matlab or any other programming language is that we can play with these numbers and see what would happen in any scenario, and that's what I'll show now. Okay, so let's see with the Matlab. So we have this code, this is the mat file here, this one here, is specificity sensitivity.m. So if you click on it and you have Matlab, this will open, and all you need to care about is this. So we'll speak about that, and that's all you need. Okay, you don't need anything else. You don't need to know how to code. You don't need anything if you don't know how to code. If you know how to code, you can follow. It's a very simple code. So what we need to know only is x. X is the population. Let's see, for example, 400. If we wanted to work with the population of the United States, we put 330 million, 123, so that's 330 million. And then the proportion positives in percentage. That would mean how many we think are positive. For example, if we think nobody has the condition, we put a 0. If we think that 1% of people have the condition, we put a 1. If we think that 2% have it, we put a 2. I'll work with 400 people only in the population in this simulation because I want to find out what happens really quickly. But it doesn't matter. You can even study this as a function of population. You don't need to care about that. All it does is calculate the number of in the 400 that will be positive and the number that will be negative. And all you need to care here is about these three things. How many cycles do you want to perform? I put here 3. If I put a 0, it means that only 1. Okay, I want to run only one. Only the test, I want to run it only once. That means when I click, it will be like I take the population and I submit them to the test once. So they take the test and some are predicted positive, others are predicted negative, and we have positives and negatives. But if I want to run more cycles, for example 3, I put here 3. Okay, now what's this? True positive rate, true negative rate. For example, imagine we buy a machine, an instrument, and the supplier tells us that it's 0.6. So that means that out of 10 people that are positive in the population, the supplier is telling us that we'll detect 6 on average, okay? And the true negative rate, specificity, is 90%, 0.9. That means that out of every 10 negatives in the population, we'll get 9 on average. So that's it. Let's run the code and let's see what happens. What we get out of this is 4 plots. The plots are here at the very end of this, but you don't need to care about that. So this figure 1, figure 2, figure 3, and figure 4, you don't need to care. All you need to do is run the code. So you open that, even if you don't know anything about Matlab, all you need to do is play this triangle here, run it. Okay, so remember that we had 400 people in the population, percentage of positives was 2, and TPR was 0.6, TNR was 0n. So and we did 3 cycles. So let's see what happened. So in the first cycle, we got 34 false positives. Okay, so that's false positive with number of cycles. This here in the x-axis is the number of cycles, and the y is false positives, FP. Okay, so first cycle 34, we did bad because we only had 8 positives because 2% out of 400 is 8. So out of 400, only 8 people were truly positive, and we got 34 false positives. But look at what happened in the second cycle. So if we submit the people that gave positive or turned out to be positive in the first round again to the test, we reduce the false positives from 34 to 1. So we got rid of almost all false positives. And in the third cycle, 0. You could say, okay, so let's keep doing that. That's not good, and you'll see why. Because, and partly it's because the true positive rate will go down. So you'll keep removing true positives also as you keep performing the test, okay? So let's see what happened here with the false negatives. They went up. And that means that we got less true negatives, okay? And that's in agreement with what I said before. So in the first cycle, 3 false negatives. So out of the 392 people that were true negative, we also got 3 negatives out of the positives, out of the 8 positives. And at the second cycle, we got 5. Third cycle, still 5. And fourth cycle, here 7. So I would say that 2 cycles would be enough, because look, at the second cycle, we removed false positives by more than 10, okay? A factor of 10, so that would be enough. 2 cycles, according to the simulation. And what happened with the true negatives? So they plateaued also at the second cycle. More or less, we got true negatives, most of them, yeah, 360 almost, and second cycle 391, and then it plateaus. So I would say 2 cycles would be enough here, submitting the people that are positive again to the test. And then what happens with the true positives? So what happens, as we can see, and that's why I wouldn't do more than 2 cycles, because first we get 5 out of 8, which is more or less the 60% that the manufacturer told us here. But then after with the second cycle, we get 3 out of 8. So that's now not that good. So we're doing worse with the number of true positives detected. Then it plateaus a bit, but then it goes down. So if we kept doing this with the number of cycles, we'll go worse. Let's see what happens if, for example, they gave us a machine that's much better in true positive rate. Let's see if we got 0.9 and 0.9. Let's run the test again. So what happens in terms of false positives? Nothing. Basically, false positives is the same, and actually it makes sense because we changed only the true positive rate. So false positives, nothing. But look at what happened with the false negatives, that we got very few, then it plateaued. True negatives also plateaus like before, but true positives improved a lot. So remember that before we were losing very fast true positives, and now we lose them slower. So as we cycle, the better we have, the better true positive rate, the slower or the less true positives we lose with cycling. So if you have a device that's very good in true positive rate, maybe it's okay to cycle 3 times. But if it's not so good, cycling twice maybe it's best, because otherwise you lose most true positives and you don't do much better in the false positives. But here, yes, here in the false positives, more or less the same as before, from 50 to 4, but we don't lose as many true positives. In any case, again, it looks like 2 cycles is still good. Okay, so with two cycles now, we have more or less the same amount of false positives, but true positive wise, with 2 cycles, we much higher. So that's good. That's what this number has done. Let's see what would happen. For example, I'll put an example that's a limiting case. Proportion of positives is 0. So nobody in the population has the condition. Out of 400 people, nobody has it. And we have this machine. Let's see what happens. I run it again. So false positive wise is the same. But look at what happens with false negatives. 0, because we don't have any positives. So it's impossible that you have a false negative. True negatives after 2 cycles already are very good. And true positives, 0. So even if nobody had the condition, it's best to do still 2 cycles. Okay, I wouldn't do many more because, as you can see, it's pointless. But if nobody had the condition, then what you would get is that you're getting rid of the false positives. But if somebody has the condition, you only think that you're getting rid of the false positives, but in fact you're also getting rid of the true positives. If nobody has it, of course it's impossible to get rid of true positives, but that's where we don't know. So if you think that the number of true positives is very low, like 1% or 2%, 2 cycles, according to this, would be enough. And that's it. I hope that you understood this experiment. And well, I want to show you now. So that was all for this video. These are the phone numbers if you want to call, and this is the email, and that's the Department of Physics and Technology at UIT, Norway, and Future Synthesis. Thank you for listening.